Here it is. So, welcome, ladies and gentlemen, to this event of the EAGE Local Chapter Netherlands. Tonight's topic is quite on the news. In fact, we are going through another lockdown apparently, and in the topic of tonight, we will talk about the impacts on reduced seismicity and climate change in climate due to the pandemic lockdowns. As usual, I will introduce a little bit the EAGE community. I will introduce, as usual, what is the EAGE local chapter and who is invited to these talks. Then I will go through the agenda of today and also to some rules about the use of WebEx event. First of all, tonight, as in our last meetings, I'm welcoming many different local chapters that are invited to attend this event. We are the local chapter Netherlands, but we usually invite also local chapter London, Paris, Oslo, Aberdeen, as well as the EAGE special interest community in decarbonization and energy transition, the Oslo Society of Exploration Geophysicists, and a few student chapters. Here you see DOGS student chapter in Delft and Aachen student chapter. For the one that don't know yet, you can follow us on LinkedIn. So we have different pages on LinkedIn about our local chapter. And you can follow there all our events and all our news about registration for new events. As well, you can contact us through email. And in our case, our email is eaglcnetherlands@gmail.com. And here are reported some of the other local chapter contacts as well. If you are not registered with EAGE, please do it. Join us. We always need more people to help us in organizing such events. Today's agenda. So the general talks are on the impacts of reduced seismicity and climate due to pandemic lockdowns, and we will have two talks. The first one starting around 6:10 on Sentinel-5P TROPOMI satellite observations, impacts of the lockdowns on air pollution levels by Dr. Henk Eskes. And the second one will be at 6:40, also a talk on global quieting of high-frequency seismic noise due to COVID-19 pandemic lockdown measures by Dr. Jelle Assink. Both of the speakers are working for KNMI. Henk Eskes is a researcher at KNMI, and Jelle Assink is a senior geophysicist also at KNMI. After these two talks, we will have, as usual, the Q&A session with some discussion. Tonight, the house rules for the Q&A are always the same. So you will have a box on the right side, and you can type your question anytime in the Q&A box, and we will read them for you at the end of the talks. Or you can also raise your hand, and the host will unmute you to have a little bit more interaction in the Q&A. So you will be able to ask your question directly at the mic. In case you want to unmute yourself, you have to click this button on the bottom. And then for the raising your hands, you have to go to participants, and then you will see behind aside your name a small hand. You can click on that, and then the host will unmute you. Or, as usual, you can just click on the Q&A box that will appear from this pop-up menu, And then you will type your question in the box and you will send them to us. At the end of the session, Dorit, that helped organizing these talks, will read them for the speakers to answer. Okay, one more thing I want to remind you before starting with the first speaker is that these talks are recorded. And that they will be posted on the YouTube channel of the EAGE. So you can review also our last events in the same place, in the same repository, and it's quite convenient. So without further ado, let me introduce the first speaker of tonight, Henk Eskes. Henk received his PhD degree in 1992 in theoretical physics at the University of Groningen. Since 1997, he is employed as a senior scientist at the Royal Netherlands Meteorological Institute, KNMI. The research of Henk focuses on the composition of the atmosphere. He is an expert on atmospheric chemistry modeling, chemical data simulation, and satellite observation of trace gases in the atmosphere. He is strongly involved in the Copernicus Atmosphere Monitoring Service, CAMS, and the coordinator of the CAMS validation contract. He is a product lead for the NO2 product of the tropomy spectrometer instrument on the Sentinel-5P satellite. So with this, I will leave the stage to Henk. Please, Henk, you can unmute yourself and go ahead. Thank you.
Thank you very much for the introduction. I think in my CV there were a lot of terms and which maybe not everyone will understand. Let me try to share my screen. Yes. So I hope you will see the slides now.
Yeah, we can see them.
Is there anything blocking the slides?
No, it's fine. You can go ahead.
Okay. Because I have a box on my screen. Good. So my talk will be about Sentinel-5P TROPOMI. I changed the title slightly a little bit. I added the word NO2 here because I will mainly focus on nitrogen dioxide in my talk. But basically the title consists of two parts, and also my talk will consist of two parts. I will first introduce the tropomy instrument and what it can do and how it observes the atmosphere. And in the second part of my talk, I will zoom into the impacts of the lockdowns on air pollution levels as measured by tropomy. And what you see on this slide is an artist's impression of tropomy flying around the Earth. And tropomy is in fact, it's not the full satellite. The satellite is called Sentinel-5P, and tropomy is on the bottom. And you can see the instrument mounted on the platform there. Oops. Okay, this is a photograph of tropomy when it was still on the ground some 5 years ago. So you can see it's quite a big instrument. It's say 1.5 meters in diameter. So it's not a small sat as many satellite missions are nowadays defined. Tropomy is an instrument which was largely built and financed by the Netherlands. So it's a partnership between Airbus, KNMI, Esron, TNO, and commissioned by NSO and in collaboration with ESA. So ESA is providing the platform which is hosting tropomy, which is the Sentinel-5P. And Sentinel-5P is a Sentinel, and the Sentinels are part of the Copernicus program. So now you have all the terms, and maybe you have heard of Copernicus before, which is a major Earth observing program from the EU. So this image when it moves, yes. So this is showing one of the big advantages of tropomy, and tropomy is able to observe the entire globe in one day. Let me start it again. just to, oops, sorry. There we go. So it's flying in a polar orbiter, so it's going over the poles, and it has 15 orbits per day. And because the swath of tropomy is very wide, it can really observe the entire globe, nearly the entire globe in one day. And when it does so, it measures several aspects, and those are shown on the right here. So in my talk, I will focus on the nitrogen dioxide measurements by tropomy. But tropomy is also helping to monitor the ozone layer, which is the second globe that you see on the right, but also other species like formaldehyde. Tropomy is measuring methane. So methane is one of the important greenhouse gases, which is monitored by tropomy. Carbon monoxide, and other important, quite long-lived trace gas, which tells you something about air pollution in the atmosphere, and also sulfur dioxide, which, for instance, has many has a major source, which are the volcanoes. So we can measure quite a big range of different gases with tropomy. Oops. Another big advantage of tropomy is the spatial resolution. Tropomy is a spectrometer, and that means that it's difficult to go to very small pixels when you want to have high resolution, high spectral resolution wavelengths resolved measurements. But here you can see how tropomy compares to previous missions, which have already been launched before tropomy and which are partly still flying. So we see footprints from Skiamaki, GOM2, and also from OMI. And you can see that many of these footprints are really quite large, so typically of the order of maybe 50 kilometers. And tropomy is really making a big step there. So tropomy was originally designed for 7x7, and that's the red box in the middle. And during just before launch and also after launch, we have further improved the resolution of tropomy, which is the blue box, which is now 3.5 by 5.5 kilometers. So with that kind of resolution, we really have detailed information, not only of regions, but we can really zoom into parts of cities and resolve individual sources of air pollution. Okay, so what's the basic principle of tropomy? So the idea is that tropomy is a spectrometer, so it measures detailed information for different wavelengths. So what you see in this graph is the visible light. So you have the rainbow, the colors, and the corresponding wavelengths of the light. And if there would be no absorption, you would basically see sort of the rainbow as you see on the top. But then if we start to add NO2, the NO2 will absorb part of the light. And then you get this very characteristic set of lines, which you can see in the graph there. And so that functions a little bit like a barcode. So if we can identify those lines and their locations are very specific for NO2, then we can really say, okay, this is what we are measuring here is NO2. And if we increase the concentration of NO2, the lines will become deeper. So if we measure the depth of the line, we have a measure of the amount of NO2. So how does this work in reality? And what I show here is actual measurements of tropomy. So it's basically one particular footprint, which shows on the horizontal the wavelength, and on the vertical the intensity that the instrument is recording. First of all, I would like to make a remark, and that's when you think about it, you would expect that it's absolutely not easy to observe something like NO2, because the concentration of NO2 is only typically one molecule within 1 billion air molecules. So it's a very tiny concentration. And so it's really a challenge to measure that. And in fact, the curves that you see are really demonstrating this, because what tropomy is doing is it's measuring directly the sun, And it's measuring the Earth, the radiation of the sun, which is reflected from the Earth's atmosphere. And the solar spectrum is the blue line here, and the Earth spectrum is the red line. And the first thing that you can notice, especially in the center, it's very clear, is that when you look at the Earth, you basically see the spectral features of the sun. And so to a very high percentage, that's all that you see. So the next thing that we have to do is divide the Earth spectrum that we measure by the solar spectrum. And that's shown in this graph. If you do that ratio, you basically get almost a straight line with a very little bit of hair and ripples on top of the straight line. And the information which we are interested in is hidden in those small deviations from the straight line. And I've shown here two examples. One is the Pacific, where we expect very little NO2, and the other is over Paris, a pixel. And there we expect a lot of NO2, but basically the ripples still look very similar. So we can blow up this straight line more and zoom into the small ripples, which we see on the straight line. And then what we get is the black line in the center. So it's the curve A in this plot. And what I plotted on top is curve B, which is in fact a reconstruction of the signal that tropomy measures based on absorption cross-sections which we obtain from laboratory measurements. And what you can see is that you can get a very, very good match of the spectra which are observed by tropomy by using this kind of lab information as input. And in order to get that fit, we have put in NO2 in this case, which is curve E, the green curve on the bottom. And you can identify some of these features, like for instance at 445 nanometer, you have these two dips, and those are typical features for NO2. So in this way, we can, what we've basically shown here is that we understand the spectra which is measured by tropomy, and we are sure that what we observe is NO2. And the interesting thing is also because we can do these fits so accurately, we can also observe NO2 over a wide range of magnitude of NO2, at least 2 orders of magnitude. Okay, but unfortunately, there are also other complicating factors which make the measurements a bit more uncertain. And we also need to know about aspects that influence the intensity of the light in the atmosphere, such as the surface properties. So what you see on this map here is the KNMI in the middle. That's where I normally work. But you can see that the city and the green grass and the forest, they all have very different surface properties. And that also influences our retrievals or our estimates of NO2. Also, aerosols in the atmosphere are important, have to be taken into account, and especially also clouds. So if there is a closed deck of clouds, we cannot look below the clouds, so we will not have measurement of NO2 at the surface. And another thing which is also important for the retrievals is that we have to know more or less where the NO2 is in the atmosphere. So what is its altitude, more or less its distribution. So that also is something that determines the final number which we get for NO2. And the cartoon here shows all the complicated processes that you have to put in. So together with our retrieval, we also run a model which provides this kind of NO2 profile information, which we also use to do the retrievals. And so that there's a lot of complicated processes involved, like all the emissions at the surface from industry, transportation, natural emissions, fires, and then all the transport in the atmosphere and the chemical reactions that take place in the atmosphere. And another note I would like to make is that, in fact, if you look at NO2, the majority of the NO2 in the atmosphere is in the stratosphere. So that's basically above 10-kilometer altitude. So that's another complication. So what we do in our retrievals is that we estimate the stratospheric amount, and we subtract that from the total signal that we get to obtain the tropospheric amount, or the amount close to the surface. Okay, and if you do all that, this is the kind of map that you get. So this is a yearly mean. It's the year 2019. It's measured by tropomy, so it's the NO2 distribution over the globe. And yeah, if you look at the color bar, for instance, you can see that indeed we have this large range of values that we can measure. So the color bar goes from maybe 5 to 80, but in fact, if you look at the red spots, they are saturated. So values go up to something like 300 or 400. So that means that we really have these 2 orders of magnitude that we can measure. And there's a lot of interesting things to show here. First of all the inhabited regions, so where we have most of the population, and especially the developed countries, they have typically quite a lot of NO2. So you can see Europe, the US, and China is in fact on a larger scale. It's really the biggest source of NO2, which you can clearly see in this image. So you can directly already see this distinction and the ratios between the different regions in the world and how they contribute to NO2. You can also see the interesting thin lines on the oceans, and these are ship tracks, so we can measure ships with tropomy. We also see in Africa, we see this region in the Sahel and also in Central Africa. And those are mainly fires, so it's biomass burning that we also pick up with tropomy. And the same holds for the Amazon region, where you see the green colors there, which are mainly fires which happen in the rainforest there. So a lot of detail, and in fact, because of the resolution, you can really zoom into this image, because we have a resolution of about 5 kilometers. So you can really zoom into the different continents and the individual countries to see all the details. Okay, I already mentioned that we have these models, and the models should be realistic. And one thing that you can do with tropomy is, of course, test your models. And what we see here on the left is the measurement of tropomy, and this is in fact for one single day. So we don't have to restrict ourselves to yearly means, but we can really do measurements for one day. And you can see holes in between in this image because of clouds. So when there is a cloud, we just have the gray color. But for the rest, you can see a lot of detail. You can see the cities like Paris and Milan, Rome, Madrid. You can see that the Netherlands and Belgium and the Ruhr area in Germany, they are really big sources of NO2. And then you can compare that on the right with model simulation. So in this case, it's from this CAMS, so this Copernicus Atmosphere Monitoring Service, which was briefly mentioned in the introduction. So it's the model, those models for Europe, which are run on a daily basis, and they can be compared for the same day. And you can see that there is quite a good agreement here between the two, between the model and the measurements. Yeah, so what I didn't tell you about is why is NO2 important, and is it such an important gas in the atmosphere? Well, in fact, it is, because for different reasons. It's for air pollution reasons, it's for the nature, and also for climate. For air pollution, NO and NO2 together, they lead to the formation of ozone when they are combined with hydrocarbons, and that's also shown in the image on the right. So there's a lot of chemical processes taking place in the atmosphere, leading to ozone formation, and ozone, especially at the surface, is bad for our health. So NO2, apart from producing ozone, it also has direct health effects. so it's not good for you. NO and NO2 are also transformed into particles, and again, particles are not good for health, and they are part of the air pollution mix that we have in the atmosphere. Then also for nature, so the NO and NO2 will be transformed into nitrate particles, and those will be deposited. And that's harmful for the ecosystem, so it leads to fertilization, but also acidification. And yeah, that's leading to a reduction of the number of species, for instance, in the nature. And then also for climate, it plays a role because NO and NO2 lead, for instance, to the formation of free tropospheric ozone, which is a greenhouse gas. Also the aerosols, they have impacts on the radiation budget. So they have an effect on the greenhouse effect. And also the lifetime of methane, for instance, is impacted by the chemistry of the atmosphere. So also there it has an impact. So NO2 is really a key compound in the atmosphere, and we need to know that quite accurately. Good, that's my introduction, and then I will continue with the second part of my talk, which is focusing on the impact of COVID-19 lockdowns on air pollution. And it has been really a very hectic year because the tropomy observations have attracted a lot of attention in the past half year. And it all started, of course, with China, because the first lockdown that occurred in the world occurred in China. And what you see here is a direct comparison of February, March 2019 on the left, which is sort of business as usual concentrations in China. And those can be compared with 8 to 28 February 2020, which is in fact more or less the lockdown period that China had. So it's a period of 3 weeks where we average the data of tropomy. And you can see that there is a huge reduction of the amount of NO2 pollution in China in 2020. So that attracted a lot of attention, and it's really a good side effect of the whole corona pandemic that we have. And so it's during the lockdowns we really see this cleanup of the atmosphere and improving, in fact, our health in that respect. So not only China, but when we move from February to March, we begin to see effects all over the world. And this is an example for India, how it looked there. And it's very interesting. Again, what we do, we compare 2019 on the top with 2020 on the bottom. And now it's about a month of data, which is averaged of tropomy. And especially if you focus on a city like New Delhi, you can see that the normal concentrations are almost disappeared during the lockdowns that occurred in India, which were very strict. But this in contrast to other things like the power plants. So you can see that some of the power plants in India hardly had any change in their intensity, which is in strong contrast to the areas, to the cities in India. So you can, because of the resolution of tropomy again, you can distinguish these power plants from the cities, and that really allows you to look at the different sectors and how the COVID crisis was affecting the different sectors. Then we can go to Europe. And again, what we do is we compare 2019 with 2020. And on the top, you see 2019, and you can see all the big cities, so Madrid, Barcelona, Paris, Milan, and Rome. And in 2020, all those, the amount of NO2 coming from those cities has reduced strongly. And on average, what we find here for those cities is a reduction of 50%. Compared to the year before. So it's really a major impact that we have from the COVID crisis. Okay, and then for the same period, we can go back to China. So again, March and April. But what we see is that the lockdown lasted about a month or so in China. And after the lockdown, we can really see the economy picking up again. And we directly see that in the NO2 concentrations. So we see that 2020 is still a bit lower than 2019. So there seems to be a clear signal that that's the case. But the difference is much smaller than it was before. So you can see how China is getting back to work, and that can be monitored from space with tropomy. Another thing that we did is also, because you can wonder, so what is tropomy measuring? It's basically measuring a total column amount of NO2. So that includes NO2 at the surface, but it also includes elevated NO2, like at 1 kilometer altitude. And so you may wonder if the surface concentrations and tropomy really show a reasonable match. And what we did here is we looked at time series for different cities. In this case, Milan, Madrid, and Paris in Europe, where we compared the time series for 2019 and 2020. 2020 is in red, from March up to the 1st of September. And we did that based on tropomy data, and we also did that based on surface observations, which are routinely measured in those cities for air quality monitoring purposes. And basically what we see is that there is quite a good match between what you see at the surface and from space. So if you look at the lockdown, which is sort of the dark gray period, you see this minus 42% based on tropomy, this reduction of 42% in Milan based on tropomy measurements. And for when you go to the surface observations, you get a reduction of 40%. So it's very similar, basically. And what we see is that after the severe lockdown, we see that the curves are getting closer together, and the reduction percentages are reduced, but we don't see a full recovery. So there's clearly a clear indication that some 10–20% reduction is still remaining, and it's showing that the economy is not fully recovering, and also people are still working at home, so we still see this impact. Good. But up to now, we have been comparing tropomy data between 2019 and 2020. And we should be a little bit careful with that, because we should realize that day-to-day variability induced by weather is quite strong. And one thing that we try to do is to estimate how big this variability of the weather is and how much it impacts the results. So what we did in this graph is for individual cities in Europe, like Madrid, Barcelona, etc. We compute the relative ratio from a modeling study between 2020 and 2019, expressed in terms of percentage, for the different months, for the different cities. And what you see is that this is not zero, but because of the changes in the weather. So what we did in this model, we kept the emissions constant. So that's not a factor in the model, but the thing that was changing is the weather, which is using actual weather analysis from weather models. And you can see that the spread that you get, so the differences between 2020 and 2019 for the monthly means is of the order of 13% for 1 sigma as a spread. But for some cities and for some months, it can be bigger, like it can go up to 40% or so. So this is certainly, when you want to do more detailed analysis and get really quantitative numbers, it's important to include this kind of weather analysis in the analysis that you're doing. Another thing I would like to demonstrate is the use of the high resolution of tropomy, and this is just one example where we look again at China and we zoom in to the northern part of China, the city of Changchun. And what you see in panel A is 2019. And you can see the highways, which are the lines going to Changchun. You see the city of Changchun. But we also have a couple of power plants there and a few industrial areas. And because of the resolution of tropomy, oops, sorry. Good. Because of the resolution of tropomy, we can distinguish these different sources. And one thing that you can clearly see in this figure is, for instance, the NO2, which is coming from the highways and which has been reduced enormously in 2020. So it's basically showing that especially the transport sector has shown very big reductions. And also the transport sector is in many countries sort of the biggest source of NO2. So in that way, tropomy can be used, because of its resolution, it can be used to identify the different source sectors and how they are influenced by the COVID crisis. Another thing that we can do is, because we measure on basically concentrations, but because we measure total columns, there is quite a direct relation to emissions, to the emissions at the surface. And this is an example of a study by Ding et al., published recently, where she used the tropomy data to estimate the reductions that happen to the emissions in China, and that's the central panel, which you see here. So basically, most of the figures in central China are really blue. So that means that there are big reductions of the order of 50% in many of these locations. So that's one important application of tropomy, is to give a better estimate of these kind of emissions and to constrain these kind of emissions in this way. Good, and you can go even a step further. So we have talked about concentrations of NO2 and emissions of NO2, but NO2, as I mentioned, is influencing the full chemistry system. So one thing it does, it has an impact on ozone, as I mentioned already before. And that's shown here on the top, in the top panels, so especially on the top left, you see the ozone response. In fact, the impact on ozone is quite complex. So you see that in the south, the reduction of NO2 leads to a reduction of ozone, but in the north, it's the opposite. So the reduction of NO2, in fact, leads to a slight increase of ozone. And that can be translated into health effects. So what you see in panel B is then the hospital admissions related to increases in ozone. And they basically give the same pattern, although it's not a very big effect for ozone in particular. The effect for aerosols, which is shown in the bottom, is in fact bigger. And for aerosols, the reduction of the air pollution is really positive, has a positive effect. So you see that there's really a health benefit from the reduction of the particles in the atmosphere. Good, that brings me to my summary. So what I've shown in my talk is, first of all, that NO2 can be observed very well from space. And we can cover a range of about 2 orders of magnitude in NO2 column values with an instrument like tropomy. There's other instruments that have similar specs as far as this is concerned. Yeah, so tropomy is observing this unprecedented sudden major reduction in NO2, which is really worldwide, happening on all continents. So that's something that has never happened before in this scale. And that's related to this worldwide COVID-19 lockdown measures. So we see really reductions of the order of 50 or 60% within 1 week. So very, very big changes in air pollution levels seen from space. And that's mainly linked to the transportation sector, so cars, trucks, aircraft, ships. These kind of observations attracted really a massive public media attention for tropomy. and also massive scientific attention. So up to, say, October, I counted at least 40 published scientific papers, which is really a lot for only half a year. And there will be many more to follow. So I lost count of all these papers in the meantime. Then after the lockdowns, I've shown that typically they last for 1 month, but when the lockdown is relaxed, concentrations start to increase rapidly. But we have indications, for instance, in Europe that it's not fully back to normal. There's still 10 to 20% reductions remaining. Yeah, so we can use those concentration observations to constrain emissions, which is a very important aim of tropomy, to get emission estimates. And we can study the impact on other air pollutants like ozone and aerosols, and also the impact on health. So that's the aim of future papers, also to make these kind of translations of these measurements to this kind of interesting quantities. And finally, that's not something I talked about, but we can also use the NOx observations when we can identify also the emission sectors. It also provides indirect information about what's happening to CO2. So that also makes a strong link to climate and how much climate is benefiting from COVID-19. Okay, thank you very much for your attention.
Thank you, Henk. Really interesting talk. As you know, we wait until the end to have questions for you. I have some questions myself because there are really interesting topic touched. CO2 is one of them, for example. But I will keep them for the end. So let me share my screen to introduce the next speaker. And Hannes, I need to share my screen. Thank you. Here we go. So the next speaker is Dr. Jelle Assink. Jelle is a senior geophysicist with the Seismologist and Acoustic Department at the Royal Netherlands Meteorological Institute, KNMI. He makes use of seismic and acoustic data for the study of these waves in the Earth, ocean, and atmosphere. His efforts have contributed to the use of infrasound for atmospheric remote sensing, the monitoring of natural hazards, and the verification of the Comprehensive Nuclear Test Ban Treaty, CTBT. For his research, he has developed algorithms for data processing and infrasound propagation modeling. Currently, he is responsible for the operations of KNMI's microbarometer array network and is interested in synergies with other measurement techniques. Before joining KNMI in 2015, he worked at the National Center for Physical Acoustics in Oxford, MS, USA, and the Alternative Energies and Atomic Energy Commission, CEA, near Paris, France. So I leave the stage to you, Jelle. Please go ahead.
Thank you, Diego, for this introduction. I will share my screen with my presentation. I hope it works. I have to admit that I used PowerPoint to prepare this presentation, although I'm usually a LaTeX user. So hopefully it works. So today I have the opportunity to present work on the global quieting of high-frequency seismic noise due to the COVID-19 pandemic lockdown measures. And this is work that culminated from a true collaboration between, I believe, 76 seismologists all around the world. Scientists from 25 countries all came together basically during the first lockdown in April, May through July to get this work together. And it was led by Dr. Thomas van der Kok at the Royal Observatory in Brussels in Belgium, who really initiated this work, and more people started to chime in. So in a way, like Henk, I will introduce this talk with some providing some context of our measurements that we have. So here the topic today is about vibrations instead of nitrous oxide. And then I will present some work from this paper that was published earlier this year in the journal Science. Okay. So let me first discuss a little bit about earthquakes in the Netherlands with you. So the Royal Netherlands Meteorological Institute, besides studying the weather and climate, also has a seismology and acoustics department, of which I am part. And one of our tasks is to monitor seismicity in the Netherlands. That in the Netherlands is mainly due to induced earthquakes that mainly occur in the north, in the province of Groningen. But there's also some in North Holland. And then, of course, there's the natural occurring tectonic events that occur in the southern part of the Netherlands. And those occur mainly due to larger scale fault zones. So these have certain names. The veldbies and the Pilrandbreuk are the fault zones that run from the southeast to the northwest. And the most well-known earthquake that occurred in the Netherlands is already dated a while back. That's 1992, which was the Roermond earthquake, which occurred here in Limburg and had a magnitude on the order of 5.8 on the scale of Richter, which is the magnitude scale for seismologists. KNMI operates a dense network of sensors to monitor for these events. These will be shown on the next slide. The network is rather dense in Groningen, in particular in response to due to the unrest that has grown due to the gas extraction and the damage that has resulted in the people's homes. So to be able to monitor these earthquakes accurately, there's a very dense network here in Groningen. In the south, there's also a network which is a little bit less dense. But this network is also able to even pick up events across the border in Germany. So these are sometimes also detected, particularly the bigger ones. Both these events are routinely being reported on the KNMI websites. So we have a 24/7 duty for this. So in fact, in 2 weeks between Christmas and New Year's, it will be my turn to have the duty phone. And if there's an earthquake occurring in the middle of the night, I will be the person doing the analysis and publishing it on the website. And if it's a really large one and it's felt by people, it of course will be reported on in the media. The data is publicly available through the websites. rdz.knmi.nl is the website of our department through which we disseminate raw waveform data, but also the event data itself. So people can also download the data and do their own analysis if they want. So as I promised you, there's a dense network of sensors. So the blue triangles here are the borehole seismometers that are mostly located in Groningen. They are installed as a string of instruments that go down to 200 meters depth. The reason for that is to reduce the amount of noise that is recorded on instruments, and that is something that will be in fact the main topic of this paper, so of this presentation. So I will discuss that a little bit in more detail later. The ones in the south, as you can see, are a little bit less dense, the network, but of course there's always a choice for about a trade-off of the size of earthquakes that you want to be able to detect and the density of the network. And for this choice, the network in Groningen is a little bit more dense. An additional aspect is the use of accelerometers and microbarometers, and that allows us for accelerometers to be able to quantify the magnitude of acceleration on the Earth's surface, which is an important parameter to know the strength and the amount of damage that an earthquake has brought. The microbarometers allow us to be able to distinguish between events that occurred in the solid Earth or in the atmosphere, Sometimes there's a military jet fighter that flies faster than the speed of sound, particularly above the North Sea. These give out of a loud bang, and sometimes that gets misinterpreted as an earthquake. So to be able to distinguish between both type of events, we do both the seismic and acoustics at our department. Well, the seismic and also acoustic, but let's focus on the seismics in this talk. Landscape is rather complex. If you have a seismometer, which is depicted in this figure in the middle, this is more of an old style seismometer, by the way. The more modern types don't have a paper and a pencil anymore. These are seismographs, but they always look nice for the people's eye. But the seismic records consist of a lot of contributions from different sources. So the one that you're interested in, of course, are the transients from earthquakes. But typically, and particularly if you install a seismometer in close vicinity to urban centers, cities, or perhaps railways, you will be able to pick up vibrations from various sources. And the reason for that is really that the seismometer is a very sensitive instrument, being able to detect displacements of a very small amplitude. And these amplitudes are really down to the order of nanometers. And that is really the key also in this talk, because of this sensitivity of these instruments, we are also able to detect the reduce of seismic noise during the COVID-19 pandemic. Now, for seismologists, the source of interest has traditionally been an earthquake. We are interested in monitoring for that earthquake, perhaps happening in Groningen. And for that reason, you want to reduce the amount of seismic background noise, because that doesn't allow you, a high amount of noise, of course, limits you in your ability to detect an earthquake. However, I would have to say noise has become more and more in fashion to image the Earth. And later on in this talk, I will present some examples of that. And it also provides an opportunity in that sense. But traditionally, it really has been a nuisance. So for this reason, seismologists tend to install stations at quiet spots to maximize the signal-to-noise conditions for recording earthquakes. And I will show an example of that. But you can really see here in this overview picture that there's a contribution from various source types. And with the densification of the seismic network, this also allows us to monitor these different source types much more accurately and use information to monitor, for example, natural hazards. A seismologist typically uses various tools to look at the recordings. One of the principal tools is something that's called spectral analysis. So most physicists will be well known with this technique. So it allows us, of course, to disentangle the recording into its different frequency spectral characteristics. So what happens if you apply a spectrogram technique to say a given seismic record for a couple of days? You typically tend to pick up several patterns in the spectrogram. So this is a figure that I took from a paper from Diaz et al. From Nature Science Reports 2017, who did an analysis of the urban seismic landscape in Barcelona. So he took a seismometer in Barcelona and looked at different frequency bands. And in the higher frequency bands, you can clearly see like a weekly pattern, which relates to human activity. Whereas in this lower frequency box between 0.1 hertz and 1 hertz, in the red box, you see activity, and that is mostly related to vibrations from ocean swells. So the oceans itself also tend to send off vibrations as well. So it's quite different, as you see from the blue box, is that it doesn't have that weekday weekend structure anymore. So this is really a natural feature compared to the weekday feature. So that gives insight in that seismometer is also a way to give information on that. If you zoom in further, you can even pinpoint individual events. So in this paper, in the same paper, the author analyzed a football match between I believe, Barcelona and Bayern Munich, where they were able to see when different football players scored, and you can clearly see that there were massive amounts of vibrations due to the crowd cheering. Now, to reduce the amount of vibration, what is typically done is to install seismometers at depth, and that was kind of alluded to before. In the north, that is done. So we have seismometers down to 200 meters depth. In the southern part of the Netherlands, we tend to install them in quiet spots, for example, in underground caves. That is shown here. This is the station in Valkenburg, which is one of the Mergelgrotten. But if you don't do that, you tend to pick up a lot of anthropogenic noise. So in this case, for example, this is a station close to the railway track. You can clearly see that the NS is more or less moving on time. Sometimes there's a cargo train here, as you can see. So it's really tricky to be able to detect an earthquake in this kind of noisy recording. This also is relevant for verification monitoring. So seismology is also used as a technique to do that, for example. So this slide shows you detections of nuclear tests in 2006 compared to a more recent earthquake in the area. And this really shows you that that in the case of high noise conditions, it's very hard to detect lower magnitude events. So in this case, this was a relatively small yield test, 0.5 kilotons of TNT. So that was still well detectable, but if you go smaller and smaller and smaller, at some point it will become more difficult. Okay, so now I'd like to switch to the COVID-19 part of the talk. So as I alluded to, a seismometer can pick up many different signals. Amongst others, the human signature around the station is well recorded. And this is something that was found, and it was initiated by my colleague Thomas Lecoq, who did this analysis first on a station in Brussels, where he showed a reduction of noise after the first lockdown occurred in March. And of course, we were inspired by this analysis, and we decided to do a similar analysis on one of our stations in the build. And lo and behold, we indeed also saw a reduction of seismic noise in the 4 to 14 hertz band, which is more or less the ideal band to study this kind of signal in, where you see a lot of signal from traffic, for example. So if you, and excuse me that I didn't include a magnitude on the y-axis here, this shows the displacement in nanometers. So the typical displacement in the 4 to 14 hertz band is typically between 10 to 90 nanometers during the week, whereas during the weekends it reduces quite a bit due to a reduction of traffic around the station. So after the 13th of March, when the Netherlands massively started working from home, you see that there's quite a reduction in seismic noise. So on average, I believe in the build, a reduction of 10 to 20% in seismic noise was measured. 45% was measured in the build, but that's because it is quite close to a highway or multiple highways, in fact. If you average this over the Netherlands, it's a little bit lower. You have also stations that are a little bit further away, of course, from traffic. So on average, I'd say it's about 10 to 20%. So of course, a similar analysis was done worldwide, and that's shown in this on this slide. So on this map, it's basically this shows the it kind of shows now the analysis that was done on various stations on the world, and on the map on the left, you see where the lockdown effect was measured. So basically, in all urban centers, you can see a clear lockdown event. So these are denoted by the red square. Where it was not detected, and that is noted by a blue square. So they often are either in remote areas, or it was not visible due to that the noise source is not present, or perhaps it was overpowered by other natural sources. This is kind of interesting to see that it's really that's really, you can really see that this is a global thing. And in fact, I will show you in a later slide that there's a wave going from China later to the west, because that's also how the pandemic spread. If you look on the right-hand side, and I don't have much time to discuss all this, is to zoom in on different stations where you see the change in seismic noise in percentage. This is a station in Brussels, for example. This is a station in Barbados. A station. This is a borehole in New Zealand, actually. So also at quite large depths, they saw a reduction in noise. And the last one is actually a station in Africa at a rather low density population area. And also there you can see that there's some reduction in noise after the first lockdown occurred. It's kind of interesting to discuss here that after about 50 days after the quarantine time started, you can already see a recovery for some of the Chinese stations, and that kind of corroborates with Henk's story on what he saw in tropomy. Now, if you put all this information together, you can clearly see indeed the lockdown effects on all the seismic stations. And you see that there's also a bit of a time difference between the different stations, which basically represents the pandemic wave spreading from the east to the west. It starts here in China, and then over Europe, eventually reaches the United States as well. Okay, this is a video that kind of shows this kind of information. So it's all put together now in a animation. You can see here the seismic noise in vertical bars. So this is still in 2019 November. So you see that this weekend pattern, but now more dynamically. And then as time moves on, you can see that at some point the bars will start to reduce. And you can already see it already starts now in China. It's March now, and it's really starting to get quiet throughout the world, in Europe, and in, of course, the United States. And so that really shows the seismic noise, the reduction of seismic noise throughout the whole world. Oh, excuse me. What is also interesting is that this reduction in seismic noise has a correlation with what we call so-called metadata. So if you take information on the mobility, which is derived from people's smartphones, and you correlate that with the reduction in seismic noise, and here a median of all the stations is taken, a median of all the measurements is taken from of the slide here. That's indicated with this black solid line, and you correlate it with the mobility data from Google and Apple. You see that there's a rather high correlation coefficient with transport data, and retail and recreation, and workplaces. And that really gives you also insights in what this reduction of noise is coming from. On the contrary, there's an anti-correlation of 0.7 with the residential noise. So people have been more active at home, but at the workplace or transport-wise, there's been less noise, and that is a good way to explain this reduction of seismic noise. What is now? So now knowing all this. Okay, that's nice, but what can we do with it? Why is this information useful? Well, it's interesting for several reasons, and I'd like to illustrate that with with one particular case here of earthquake detection in Mexico. So one of the things I'd like to mention here is that a lot of this study was conducted with local seismometers. Of course, there were also the more traditional network was involved, but a lot of data was also become available because of the presence of these low-cost seismometers that are basically based on a Raspberry Pi computer with a simple geophone. And these stations are now being deployed all over the world, and data can be accessed rather easily through web services. So for one of the stations in Mexico, and that's this slide, this shows a clear case of what the reduction of seismic noise brought to enhanced earthquake detection. So in this case, you see in the upper frame A, you see there's reduction of seismic noise, as was presented earlier. In late 2019, for example, in the high noise time, it's rather hard to detect a magnitude 5 event, which is a rather large event. But during the seismic lockdown, or during the COVID-19 lockdown, it's quite easy to detect a similar event at the same station. So we understand the seismic noise around the station better. That also allows us to understand the area better, but it also helps us to understand seismicity better in the region. So knowing noise is also useful because that also allows us to eventually, having knowledge about that noise, use it for all kinds of things. And in recent studies, it has already been shown that seismic noise, for example, from ocean waves, can be used to image the Earth itself. So get an idea of what the group velocity is, but also, for example, what the temperature is at very large ocean depths, and many more studies than these have been published in the literature, of course. But this really shows you that noise can be used, and it is to be foreseen that having much more knowledge about the noise around the station, we will be able to do similar studies and bring us further at the station level as well. Moreover, having knowledge of noise around the station or around a certain site can also allow you to monitor a certain source much better than before. For example, you can try to use seismic noise around a volcano to study the activity of the volcano itself. And that, for example, was shown in a study by Brangrier et al. 2005. So perhaps we'll see in the near future all kinds of studies showing up that will benefit from the enhanced knowledge of noise around a seismic station. So that's kind of what I wanted to discuss today. This is one of the last slides that I want to leave you with. It kind of gives you a timeline of the seismic noise from the beginning from November 2019 through about now. So this is about a year worth of seismic noise data. So you see, indeed, first the Christmas break from 2019-2020. Then there's the first lockdown. Then there's this recovery of seismic noise, and then I guess there's a sudden second reduction, perhaps the holiday break, and then an increase again, and we'll see what the future brings. So with that, I would like to thank you for your attention, and any questions I'd be happy to answer. Thank you.
Thank you very much, Jelle. Really interesting talk as well. Both of the speakers tonight gave us really interesting talks indeed. So I will ask Dorrit now to open Q&A session, so she can maybe read any questions for the speakers, and then we can have some discussion about it.
Yeah, also hello from me to everybody. I have first a question for Henk from Apostopheles, and he's quite curious about what was it allowed the resolution increase mentioned in the beginning. Was it due to hardware, or was it because of different processing done in software?
Yes, you can hear me?
Yes.
Yeah,
Yes.
it's part of the whole design of tropomy. So it's also the amount of light which is captured by the instrument. It is quite a big instrument, and being quite big, it can capture more photons, and therefore also it can deliver smaller footprints at the surface. So that's the basic idea. So especially the amount of light which is captured by the instrument is bigger than other instruments.
There's another question for you. Can the vertical profile of the NO2 concentration be determined instead of the just column values?
No, that's unfortunately not possible. There's a little bit of profile information in the spectra itself, but that's a very tiny little bit. So we have sort of 1.2 pieces of information in the vertical, which is a little bit more than one, and one would be just the vertical column. So we need to, for instance, I mentioned that we need to estimate the stratospheric amount. So that's something that we do because the stratosphere is much more homogeneous. Although there are variability in the stratosphere, which is also important and which we also try to estimate. But we can use the difference in the spatial distribution to distinguish stratosphere and troposphere. And so we use additional techniques to do that, but not directly from the spectra itself.
Okay.
Can I ask something related to this?
Yeah, sure.
So, because I had in mind the same question actually, and is it possible to have some measurements from the ground, like instead only from the satellite?
Yes.
Also have something from the ground, and in this case, you have an interaction of information from the top and from the bottom, and maybe you're able to convolve the information that is along the profile. Is that possible?
Yes, combining it with the satellite, that would also be interesting. But that has not been attempted yet. From the ground, we have remote sensing ground observations, and especially you have an instrument called MAX-DOAS. And this is an instrument which is also a spectrometer, so it's measuring NO2 in the same way as tropomy does, but it does it from the surface. And but the interesting thing there is that it looks at different angles, and that's a little bit going in your direction. And so it's starting with say 1 degree elevation from the surface, and then 2 and 5, 10, up to 90 degrees. And that gives you additional information, and in that way you get some information about the profile. But in practice, it turns out to be still pretty difficult because the paths are also not the same, and so the amount of clouds in the different paths is different. The amount of aerosols can be different, so the situation can be different. The surface is different for the different paths. So combining those paths is still a very tricky business, but in that way you can get maybe 3 or 4 or few subcolumns, let's say, for NO2.
I asked that because I know that in meteorology you can measure the brightness temperature, different directions, so arrivals,
Yes.
and from that you can do some tomography and have a pattern or a grid with different values. So maybe you can do something similar also here.
Yeah, one thing I should mention is that you have satellite instruments that measure the profile in the stratosphere for NO2. So that's something that's possible. But they cannot really go into the troposphere. So we are really interested in the lowest kilometer. And this kind of limb observation from satellite is only possible for the higher layers and not for the close to the surface.
Okay, thanks.
Yeah. But maybe a tomography idea would be interesting to consider, yeah.
Yeah. I have a question. I'm not so familiar with NO2. So what are actually the health effects which are caused by NO2? Could you
Yeah, I
just name
mentioned,
some?
I have them in one of my slides. I gave an overview. So there is direct effects. So there have been health studies directly linking NO2 concentrations to hospital admissions, for instance. So there are.
But what are you getting? You're getting breathing problems, or you're getting?
Yeah, it's a mix of long-term and short-term
Okay.
problems. So short-term, it's really breathing problems, but long-term it's much more complicated. It can be heart failure. It can be your lungs, but also the skin or your. So there's many. Basically, the whole body is affected by air pollution. That's the
Yeah,
idea.
that's for sure.
Yeah. So especially also diseases of the blood system is so cardiovascular things are linked to air pollution. But often it's also because of aerosols, so it's the small particles that go into your body and really penetrate your body. So for NO2, it's the direct effect, but also indirect effects. So NO2 is producing ozone, and ozone is very reactive and is bad for your lungs and for your body. And long-term and short-term exposure is important there. But also the formation of particles, and so the mix of aerosols that we have, particles, fine particles in a country like the Netherlands is for quite a big part made out of nitrates. So they play quite a substantial role there, and so they also cause inflammation in the body. I'm not a health expert myself.
No, I just was wondering.
So it's different indirect and direct reasons why it's bad for health.
Yeah. Okay. And we saw clearly that it was reduced during this NO2 was reduced during the pandemic lockdown.
Yes.
But are there actually, do you know any what is the industry or people actually doing to reduce this gas, or are there any regulations?
Yeah, there's a lot of regulations. For instance, for cars, you have all the Euro standards for cars, for instance, in Europe, Euro 6, 5, 7, or whatever.
Yeah, but we saw that actually if you don't use a car, it's of course better. But are there
So yeah, for the diesel cars, they traditionally they produce quite a lot of NO2. So you have the catalytic converters and ways to remove the NO2 from the exhaust. And the same thing happens for factories, where also if you have a power plant, for instance, with coal-fired power plants, they also have to spend quite some investment in getting rid of the nitrogen dioxides from the exhaust. So that's, and in fact, if you go to the Netherlands and you look at the coal-fired power plants, they have very little signature in NO2. But if you go to South Africa, you see a huge NO2 signals coming from the power plants there. So basically, those power plants are not cleaned up, and it's really causing loads of NO2 there.
Yeah.
So it depends very much on the country and on the technology that is used.
Yeah. Okay. Thank you very much. So maybe we should go back. We should go to Jelle. Actually, I have a question for you, mainly because you said that there was an earthquake during the pandemic lockdown in Mexico. Were there any little earthquakes in Groningen? Just out of curiosity.
Yeah, I'm sure they have been. I do have to say, maybe that's also good to mention, is that in Groningen, because the network is so dense, as you well know, Dorit, as you work.
I know, yeah.
The higher seismic noise typically doesn't really impact the operations in Groningen that much, because the network is so dense. Huh? But in the case of Mexico, for example, the network is far less dense, and then it may be better or it may be worthwhile to have a lower seismic noise. maybe the same situation will be the case, for example, in the southern part of the Netherlands. So in the southern part of the Netherlands, there are also earthquakes that can be rather small, and of course the smallest ones you're not able to pick up because the network does not have so many stations. Yeah.
Okay. Yeah. Thanks. Yeah, you're probably right.
I also have a question for Jelle too.
Yeah. Please go ahead.
So I was fascinated by all these maps with the bars going up and down, and I'm wondering if you sometimes try to interpolate these things in order to have a map covering all the area, right? So maybe you have some models of propagation and you can apply something and to interpolate in a, of course, model-based approach or something like that.
So you mean like interpolating between the histograms that were shown in that animation?
No, I mean between the stations, in order to have a map that is covering more geographic area, let's say.
Yeah. I think the danger with such an approach would be that you would assume that in other stations where you don't have data, things occur are an average between the two neighboring stations, and I think between countries the measures can be quite different. Although I think it will be very interesting, for example, to see how, because we didn't do this analysis, for example, on a European scale, or we do it on a global scale, but we didn't do the visualization on a European scale. It will be interesting to see how different Sweden, for example, would be compared to the rest of Europe, because Sweden had such a different take on
approach. Yeah.
So
I was.
Sorry, go ahead.
I was not thinking to average, like a mathematical average, but maybe to run some modeling based on the general properties of the areas and try to combine these and to see if it's possible to extend the information a little bit more, not only locally at the source location, but a little bit more around them, let's say.
Yeah, for sure. It's. I think that. Yeah, it's. I don't think it has been done yet, but I think it would be very interesting to see how it's within a country, for example, how it's, because within a country the measures are the same.
Yes.
You could see indeed if there's more of a flow of information. Yeah.
Okay.
Can I also ask a question in relation to this? I think it's an interesting question, but but you already mentioned that sometimes the noise is coming from a source very close to the station, like if you have a railway station, you can see it. So it really depends on how far this noise travels and how. Can you give any indication of a typical distance that such noise is coming from?
Yeah, it's typically a few kilometers. So it depends. It depends very strongly on the attenuation of wave energy. That depends a lot on the subsurface. But what you tend to see is, it's certainly at these frequencies, is that you pick it up over, say tens of kilometers, and then it's falls below the noise. Wind noise, noise from wind turbines is another aspect, for example, that we often pick up on our seismic network, and that is typically also seen within, I would say, up to 10 kilometers, maybe a little bit further.
Okay.
That also has a similar frequency band. But if you go to very low frequencies, below 1 hertz, that can be thousands of kilometers. Yeah.
Yeah, I don't have any further questions here in on my list. Sorry. So maybe we should wrap it up, Diego.
I think there is one that just popped up now. Maybe we can read this one before leaving.
I can't see. Oh, in the chat? No.
Yes.
Okay.
Do you see it, Dorit? Do you want me to read it?
I cannot see it, sorry.
I can read it.
Chat
So,
in the Q&A.
It looks like the induced seismicity in the Ruhr area is larger than in Groningen. I never heard of complaints from the inhabitants of the Ruhr area. Is that lower surface acceleration, stronger houses, or more resilient people? It's the question for Jelle, I guess.
That's a very, very good question. I have to admit, I'm not a domain expert on it. It is indeed significant. We often pick up these events. They're often large. A lot of them have to do with mining, so surface mining. So that could explain part of it. Whereas in Groningen, these events occur at depth, at 3 kilometers depth, which is already rather shallow. Also, the soil properties are different, but I wouldn't know about the amount of complaints in Groningen versus the Ruhrgebiet if people have done comparative studies to that. So, but we do pick up a lot of these kind of mining events. That's true. Yeah.
Okay.
Good question.
Thank you very much. So, if you agree, Dorit, we will close here the Q&A.
I agree.
I will just show you a few more slides about, well, the acknowledgements, I guess. And can I share my screen, Hannes? Okay. So yes, today just the acknowledgements slide here. So I want to thank, of course, Henk and Jelle for the interesting talks and discussion. It was a pleasure to have you with us. So thank you very much for accepting our invitation. As usual, I want to thank Ramco Versi for providing this WebEx event platform to host these events. And all the EAGE family, special interest community in decarbonization, energy transition, the local chapters of Aberdeen, London, Netherlands, Oslo, Paris, the OSEG, and the student chapter DOCS and RWTH Aachen for their participation. A special thank tonight also to Dorit that helped us in organizing this event, contacted the speakers, and as usual, I'm very thankful of having Hannes that is always helping me with the event organization and also setting up the WebEx event platform. So with this, I can stop sharing the screen and yeah, thank you all for and see you soon.
Bye-bye.
Bye-bye.
Thank you.
See you.
Bye-bye.
Thank you.
Thank you again.